Assalamu alaikum.
Walaikum salam, sir.
Walaikum salam.
Okay, so welcome to the class of microwave engineering. Hopefully, everyone can hear me clearly.
Yes, sir.
Yes, sir.
Okay, so it's lecture number 3. So, in initial 2 lectures, we haven't covered too much stuff regarding microwave engineering. It was basically the introduction of microwave engineering, the importance of microwave engineering for any electrical engineer, and then also I revise some of the topics that you people have covered in the prerequisite course, that is EMF, and I specifically ask you to revise coordinate system and Maxwell equation. uh, I also make sure that you understood the coordinate system concept and Maxwell equations from that particular aspect, which is important for microwave engineering. So today we are going to talk about another important topic that I am not 100% sure that but maybe you might have covered that as well in your previous course of EMF, and that is boundary conditions. So let's go through what is boundary conditions and what is their use in microwave engineering. So in my last face-to-face lecture, I wrote down the mathematical form of Maxwell equations. So we have a point form of Maxwell equation as well as the integral form. So if you look at the point form of Maxwell equations, so basically they are differential equations. And from your knowledge of differential equations, you know that whenever you are asked to find the solution of differential equation, so whenever you solve any differential equation, you will always end up with some unknown constants in the solution. And in order to find the values of those constants, you require some conditions. Okay. So from Maxwell equations point of view, whenever you solve Maxwell equations, you will have some unknown constants in the solution. And in order to find the values of those unknown constants, you require some conditions, and those conditions are known as boundary conditions. So that is the mathematical background of why we require boundary conditions. Okay, so the point that I am raising is to find a complete and unique solution Maxwell's differential equations. We require boundary conditions. And the other point is where you will require boundary condition, what type of problems we will solve that will require boundary conditions. So whenever there is a boundary or interface between two different media, so let me write it down. Whenever electromagnetic wave travels from one medium to another medium, the change in fields is governed by boundary conditions. So this is the background of boundary conditions. Now, what are the mathematical form of these boundary conditions? We will derive these boundary conditions by making use of Maxwell equations. Okay, because uh, whether we are talking about Maxwell equations or whether we are talking about fields, so we all know that Maxwell equations are fundamental equations that must be satisfied by any field. So in the same manner, when electromagnetic wave consisting of electric field and magnetic field, whenever it moves from one medium to another medium, so the change in the fields, it must be according to Maxwell equations. Okay. So let me draw a figure with respect to which I will write down or derive the boundary condition. So just like for Maxwell equations, we have four boundary conditions. So by making use of four Maxwell equations that I devised in my previous lecture, we will end up with four boundary conditions. So let me draw first the figure with respect to which I will be talking about different fields. So let's assume that this is some kind of a boundary and on the bottom side of this line, we have medium 1, and on the other side, we have medium 2. And in my last lecture, I mentioned that medium is characterized by some properties. So two important properties are the permittivity. So let's assume that this medium has permittivity epsilon and its permeability is mu. Similarly, this is medium 2. And why I'm calling it medium 2? Because this is some kind of a medium which is different than medium 1. So it will have its own properties. So let's assume that epsilon 2 is the permittivity of this medium and mu 2 is the permeability of this medium. So this line, as I was talking about, this is the boundary. So on one side of this boundary, we have medium 1, and on the other side of this boundary, it has medium, which is characterized by its own properties. Now, what are the possibilities? What will be there on this? Again, make sure that you look at this figure, that this line that I have drawn, it's not a line, it's a kind of a plane. You can assume as if this is kind of a plane. So there are possibilities that we will have charges on this boundary. So let me represent that on this boundary, there is a possibility that there are charges. These dots are representing charges. So we know that charges are represented by symbol rho. And because these are on the surface, so I will call it rho s. Okay. Rho s. What is rho s? Rho is the symbol for electric charge, electric surface charge. So electric surface charge density. So how many charges per unit area are there on this surface? They are represented by rho s. Now there is a possibility that these charges, some of charges may be in motion. So it means we will have charges in motion, which means that we will have a current as well. So let me represent the current by this arrow, and the symbol that I will use for current is JS. JS. And what is JS? As we have mentioned before, J is the symbol for electric current density, and because I'm writing as JS, so it means this is surface charge density. Surface current density, sorry. Surface current density. So current per unit area is represented by this. And just to complete the discussion, we also mentioned that theoretically there is a possibility that we will have magnetic current density as well. So I can represent the magnetic current density by this double arrow. So this is the symbol for MS. You will already remember that I used this symbol in Maxwell equation as well. So this M is the symbol for magnetic current density. So this is magnetic current density, which is not a physically realizable quantity. Okay, it is just a mathematical quantity. So what I have done is I have considered a general situation that at the boundary between two media, there is a possibility that we will have charges, we will have electric current, and we can have magnetic current. Now with this, what are the four quantities that I want to relate using boundary condition? So one of the quantity that I will find the relationship is that on this side of the boundary, there can be a electric flux density. Electric flux density, if you remember, the symbol that we use for electric flux density is D. And if you look at the direction of this arrow, it is taken as normal to the boundary. Okay, so the arrow is normal, so it means this arrow is representing the normal component. So I will represent it as D with a subscript N to denote that this is the normal component of the electric flux density in medium 1. And because it is in medium 1, so we will represent it by dn1. Now I want to find out what is going to be the normal component of electric flux density on the other side of the boundary. So I'm interested in finding out dn2. So the boundary conditions will tell us what is the relationship of dn1 with dn2. In a similar manner, we will find out what is the relationship of the normal component of magnetic flux density. So again, I'm going to draw it in such a manner that it is normal. So this is now magnetic flux density and its normal component. And because it is in medium 1 area, so I will call it Bn1. and I will going to find out what is going to be its relationship with Bn2. So whether Dn1 will be equal to Dn2 or whether they will have some other relationship, we will find it out in a short while. Similarly, I will be able to find out the relationship of Bn1 and Bn2. So these are the normal components. Okay, so what are the other two boundary conditions? So let me also denote the normal direction by this unit vector n. So this n with a hat is representing the direction that is normal to this boundary. Okay. So what are the other two components that we will find out? That is, I'm also interested in finding out what is the relationship of the tangent component. So let's assume that this is the arrow, and you can clearly see that the arrow that I have drawn is now in such a way that it is parallel to this boundary or tangent to the boundary. And this arrow is going to represent the electric field E and its tangent component. So we will denote it by E with a subscript T. And then again, this is in medium one side, so we will call it ET1. So what is ET1? ET1 is representing the tangent component of the electric field, which is uh, in medium one side. And we are going to find out its relationship with another tangent component, that is ET. And because now we are in medium 2, so we are going to recall it ET2. So what is ET1? Tangent component of electric field. And what is ET2? It is also tangent component, but ET1 is on at the bottom of this boundary, and ET2 is at the top of the boundary. Okay. And similarly, we will be going to find out the relationship of tangent component of magnetic field, ET1 with, sorry, HT1 with HT2. So as I mentioned, there are four boundary conditions. So now you know that what are those four boundary conditions. One boundary condition will relate uh, D1, DN1 to DN2. Second boundary condition will relate BN1 to BN2. Third boundary condition will relate ET1 to ET2. And fourth boundary condition will tell us the relationship between HT1 and HT2. So let's start with the first boundary condition, and that is, what is the relationship of DN1 with DN2? Okay. So for that, I will move to the other figure. So what I'm going to do is I'm going to draw the same boundary, but now focusing only on DN1 and DN2. So what we have is, this is the boundary. This is medium 1, medium 2. So in order to find the relationship, what I'm going to do, I'm going to use the first Maxwell equation. So what is the first Maxwell equation? That is the Gauss's law for electric flux density. That is, electric flux passing through any closed surface must be equal to the charge enclosed by that closed surface. So this is the Maxwell equation, which we revised in our previous class. Because I want to relate dn1 and dn2, and because electric flux density is it has to follow this Maxwell equation, so I have to use this. So in order to use this equation on dn1 and dn2, you see that I need to have a closed surface. because this Maxwell equation is telling us that electric flux passing through a closed surface. So what I can do is I can visualize that there is a closed surface having shape of a cylinder such that half portion of that cylinder is in medium 2 and half portion is in medium 1. You can see that I am drawing a cylinder which is a closed surface in such a manner that half portion of the cylinder is in medium 1 and half portion is in medium 2. So now this is the height of the cylinder. Let me call it h. This is the height of the cylinder. This is representing the surface area, so let's call it delta S. So now if you go back, this is the direction of dn1 and dn2. So with respect to this cylinder, what we are going to find out is how much flux is entering this surface, this closed surface, and then how much flux is coming out. So I'm considering this case number 1, and you can clearly see this is dn1 and this is dn2. So with respect to the closed surface, I have represented this dn1 and dn2. Now because this is our boundary, I am interested in the behavior of dn1 and dn2 at the boundary. Okay. So what I can do is I can transform this cylinder in such a manner that it is projected on the boundary. So it can only project on the boundary if I assume that this height of the cylinder is almost equal to 0. So what I'm going to do is, let me write it down that I'm going to use this equation to this particular case. But what I'm going to do is I am going to apply the limit, and my limit is that the height of cylinder is so small that it is almost equal to 0. So now, can you visualize this thing that when you make this h equal to 0, so what will happen? What will happen is that this cylinder, it will be just like this. So we will have only this area, it as this is dn1 and this is dn2. So when you make h equal to 0, it means that cylindrical surface, the site area, it becomes equal to 0. So only area that is going to be included in the flux is this one, which is having an area of delta S. So now what will happen to this integral? How much flux is passing through this, coming out of this? So this flux dn2, you can see this is pointing outward and this dn1 is pointing inward. So how much is the net flux coming out? It must be the flux which is coming out minus the flux which is going out. So going in, so I will say this equation will become dn2 delta S minus dn1 delta S. So the left hand side will become like this, and it must be equal to the right hand side. And what is right hand side? The charge enclosed by this surface. So how much is the charge enclosed by this surface? So how much is the charge density? Rho s. These are the number of charges per unit area, and the area that we are considering is this much. So how much charge will be enclosed in this portion? They must be equal to rho s delta s. So this delta s cancel out. So we end up with dn2 minus dn1 equal to rho of s. So what this equation is telling us, actually this is the first boundary condition. And what this boundary condition is telling us, that the difference between the normal component of electric flux density at any boundary must be equal to how much is the surface charges at the boundary. So dn2 minus dn1 will be equal to rho s. Now it means that how much is the difference between dn1 and dn2? It is dependent on rho s. So if we have a situation where there are no charges, on the boundary, we have a situation that we have two different medias, but at the boundary we don't have any charges, then according to this equation, the right hand side will be 0, which means that dn2 must be equal to dn1. So it means there will be no difference in the normal component of electric flux density at such boundary. Okay. Now, this is our equation, our desired first boundary condition, but it's always better to write this equation in a vector form. So as I've already mentioned that dn, why I'm calling it dn, because this is the normal component. So actually we have, uh, let me go back. On this side we have vector d1, and on this side we have vector d2. Now this vector can be in any, it can be pointing in any direction, but it may have one component that is normal, and that is why I've represented this by dn1. What is dn1? dn1 is the normal component of d1. What is dn2? dn2 is the normal component of d2. Now we have already represented, we have already drawn this vector n. This vector is the unit normal vector. What is this? N. This is representing unit normal vector. Normal to what? Normal to boundary. So if d1 is given to me and I am asked to find out what is the normal component, so I can take the dot product of this and it will give us the normal component. So what I'm going to do is I can write this thing in this manner, that is unit vector n dot product with d2 minus unit vector n dot product with d1 must be equal to rho s. And this is our first boundary condition. This is your first boundary condition. It's also important that you can interpret this equation. As I mentioned in my introductory lecture, that I don't want you to be able to derive boundary condition or any other equation that we will be covering in this course. My concern is that you should have conceptual knowledge or understanding of that equation. So this first boundary condition is telling us that the difference between the normal component of electric flux density at any boundary will be equal to the surface charge density. Or you can also interpret this equation as, you can say that the normal component of electric flux density will be discontinuous. The normal component of electric flux density at the boundary will generally be discontinuous. And discontinuous means that it is equal to something, and this rho s is generally a non-zero number. Okay, let me uh, say in a different manner that if you have a situation like this, that n d2 minus n d1 is equal to 0. Why it is 0? Because there is a possibility that in some cases at the boundary we don't have any surface charges. So then we will have this situation. So how you will describe this equation? We will say that normal component of electric flux density is continuous because it is equal to 0. It means it is continuous because it means that there is no difference between n dot d2 and n dot d1. So it means they are continuous. So as uh, electromagnetic wave move from medium 1 to medium 2, the normal component of electric flux density, as it passes through this boundary, it doesn't change because it is equal to 0. But in this case, in a general case, you can see it is not equal to 0. It is equal to rho s, and rho s is generally not equal to 0. So you will say that normal component of electric flux density may change, and may change means that it is discontinuous. In a similar manner, now we are going to derive the second boundary condition. And now we are going to find the relationship between normal component of B1 and normal component of. So again, I'm going to apply a Maxwell equation. And now which Maxwell equation we can use? The equation that relates to the magnetic flux density. So as per Maxwell equation, the total magnetic flux passing through any closed surface is always equal to 0. And this is basically Gauss's law for magnetic field or magnetic flux, which we have already discussed. So now, again, in order to apply this equation, I have to consider a closed surface. So the appropriate closed surface can be again the same cylinder, such that half portion of that cylinder is in medium 1 side and half portion is in medium 2 side. So this is, let's say, height of the cylinder, and this is again the area. Now, because my concern or my goal is to find out the behavior of B1 and BN2 at this region. So I can apply, again, I can use the limit that the cylinder that I'm considering is such that its height is very, very small, so that it is almost placed at the boundary. So you can say that there was a cylinder like this. When you reduce its height, it becomes like this. You further reduce it, it looks like it. So in the limit, almost when height is 0, it will be just like this. So what I'm going to do, in the same manner, I will say in the limit h approaches to 0. So what will happen to this integral? How much flux is passing through this? So this is Bn2, this is Bn1, and this is delta S. So you will say Bn2 delta S minus Bn1 delta S equal to 0. Delta S can be taken as common, and then it can be the shifted to the right side, so it will become 0. So again, we end up with Bn2 minus Bn1 is equal to 0. And again, I can write this equation in a vector form. So I will say unit vector n and its dot product with B2. So unit vector n dot product with B2 is going to give you the normal component, which is this one. Similarly, unit vector n dot product with B1, and this thing is equal to 0. Now this equation is over second boundary condition. So what is the meaning of this equation? This boundary condition is telling us that the normal component of magnetic flux density will always be continuous. The normal component of magnetic flux density is always continuous. So as wave move from one medium to another medium, the normal component of magnetic flux density will not change. Bn2 is equal to Bn. Okay. So, so far what you have seen is, it's again the meeting time is almost finished. It's less than 1 minute remaining. So we will continue with this lecture in the next session. But what we have done so far is we have derived two boundary conditions by making use of two Maxwell equations. Okay. So let's move on to the next session.